In a galaxy far, far away, two aliens named Zeeble and Horus are on their first mission in outer space. They are tasked to fly in their spaceship to planet Potato to deliver an important message about the state of the universe. To get there, they must navigate through outer space, which they think of as 3-space, by using understandings of vector-valued functions. At first, their flight is going very smoothly, but then suddenly, they are informed by their leader on their radios about a large asteroid flying through space on a space curve that is heading their way. They need to strike it with a laser beam when it is near, but to do so, they must program the position and velocity vectors of the asteroid into their laser machine. Their leader has already found the position vector of the asteroid, which is r equals 3t squared e to the t natural log of t. But before she is able to tell them the velocity vector, they lost radio signal. Zeeble becomes terrified by the thought of getting hit by the asteroid. Without knowing the velocity vector of the asteroid, how will they be able to destroy it with the laser? But Horus is not scared. He remembers learning about vectors in his outer space calculus class, and knows that the velocity vector is simply the derivative of the position vector. Look at this, says Horus. To find the average rate of change of position of an object flying on a vector between 2 points in time, we just find the difference between the positions at each of those times divided by the change in time. Zeeble is still confused. What does this have to do with velocity? Well, the average rate of change of position is the average velocity. And we remember from Outer Space Calculus 1 that the instantaneous velocity is found by taking the limit of this equation while h approaches 0. So if we take the derivative of the position vector, we will know the velocity vector. To compute the derivative of the position vector r equals x, y, z, we take the derivative of each part. So r prime equals x prime, y prime, z prime. Oh, that makes sense, says Zeeble. Horus quickly uses this derivative equation and the position vector of the asteroid that they got from their leader to find the velocity vector of the asteroid. The velocity vector is 6t e to the t 1 over t. They program the vectors into their laser machine, and when the asteroid gets near, their lasers activate it and destroys the asteroid. They assumed that after this scare, the rest of their trek would have no problems, but it wasn't long before they ran into their next obstacle. They must stop for fuel on a nearby moon that is also traveling on a space curve, and they already have the moon's velocity vector programmed into their navigation machine. But they don't know where the moon is. Their leader forgot to give them the moon's position vector, and their radio is still not working. Horus, what are we going to do? Without the position vector, we will never find the moon, and we will run out of fuel and crash and die. Zeeble begins to sob violently. Zeeble, calm down. Luckily, Horus remembers from outer space calculus that the position vector is simply the indefinite integral of the velocity vector. To integrate a vector, you can simply take the derivative of each component functions of the vector. They know that the moon's velocity vector is v equals negative 2 sine of 2t plus 2 cosine t, 1 minus 1 over 1 plus t. So to find the position vector, Horus computed the indefinite integral as shown. But wait, says Horus, when computing an indefinite integral of a vector, we have to add a constant vector c at the end, and I don't know how to find c. Oh, I know, says Zeeble. I remember that when we left, the position of the moon was at point 1.5, negative 1, 0. So we know the position at t equals 0, and we can plug in these values and solve for the c vector. So they did just that. They found that the position vector is r equals cosine of 2t plus 0.5, 2 sine of t minus 1, t minus natural log of 1 plus t. They programmed this vector into their navigation machine and found the moon and landed to get fuel and snacks, of course. Now they are ready to head on their way. Luckily, the rest of their trip will be along a new space curve that glows in the darkness of outer space, so they can follow it like a cool space road. They see the curve ahead and see that it is labeled r equals 5t, 5 sine t, 5 cosine t. The sign also says that the space curve takes 3 hours to travel from end to end. Horus and Zeeble want to be sure that they have enough fuel to reach planet Potato. But to know this, they need to know how long the curve is. Horus doesn't remember anything about the arc length chapter in outer space calculus, but luckily, Zeeble does. Zeeble begins to explain the idea behind calculating an arc length of the vector. Well, it's easy to find the length of a straight line, right? And a curve isn't a straight line, and one straight line approximation would not do a very good job at estimating the arc length. But if we break the curve into a whole bunch of teeny tiny segments, and then approximate each of those with a straight line and add them up, we can approximate the curve. The smaller the segments, the better the approximation. So we want to make the segments infinitely small. Horace nods. It's all coming back to him. Oh yeah, so we use the distance formula to find the length of each segment and then take the sum of all those lengths. I remember the formula for arc length is this. Because r prime is a velocity vector, so this is the integral of the lengths of the segments of the velocity vector. Perfect. So we can plug the vector of the road into this equation and evaluate from t equals 0 to t equals 3, which is the time it should take to travel the curve, like this. So then we get that the arc length is 7.07 utils, which is a measurement of distance in this galaxy, of course. Great, now that Horace and Siebel know the arc length of the road, they know that they have enough fuel, so they are on their way. Everything is going smoothly, and Horace begins to think about the wonders of vectors. Siebel, he says, I know all curves are curvy, but some curves are curvier than other curves. Isn't that crazy? If only there was a way to quantify how curvy a curve is. Then Siebel says, boy oh boy, Horace, do I have some news for you. We can measure how curvy a curve is. First, you have to find the tangent vector to your curve, which is just the derivative of your vector. Then you want to find the direction of the tangent vector. To do that, you have to find the unit vector of the tangent vector using this equation. This gives a vector that is the same as a tangent vector, but with a magnitude of 1, because we only care about the direction, not the magnitude. So we know that a curve has a different tangent vector at each point along the curve. So by looking at how much these tangent vectors change while traveling on the curve, you can know how curvy it is. So we can use this formula. This equation essentially tells us the magnitude of how much the direction of the tangent vector changes over the magnitude of the velocity. So if the tangent vector is changing a lot as it travels the curve must be very curvy. Look, we can measure the curvature of the road we are on like this. Thus, the curvature of this road is 1 over 10. Wow, says Horace, that is so cool. Thanks for teaching me about curvature. Horace and Siebel continued along their journey, happily thinking about the idea of curvature. They finally look ahead and see the solar system that planet Potato is in the distance. They are almost there. They can see the planet orbiting around its sun on a space curve. Siebel begins to wonder, Horace, are we sure we are able to land on the planet? It looks like it's moving really fast, and what if it changes directions or starts moving at a different angle just before we land, and we miss it? Don't worry, Siebel, we know exactly how planets move, all thanks to Kepler's laws of planetary motion. We don't have to worry about it moving in weird angles because we already know the shape of the planet's path around its sun. Siebel is still confused. Who is Kepler? What are his laws of planetary motion? Horace begins to explain. Kepler was an Earthling who studied the planets long, long ago. He used some really cool math to prove these 3 laws about planetary motion. A planet revolves around the sun in an elliptical orbit with the sun at one focus. The line joining the sun to a planet sweeps out equal areas over equal times, and the square of the period of the amount of time it takes for the planet to make one revolution around its sun is proportional to the cube of the major axes of its orbit. So we know so much about how the planet moves, specifically that it always moves in an elliptical orbit. So it can't just change its orbital shape randomly. Siebel thinks this is a good explanation, but still has questions. How could Kepler be so sure? Horace continues to explain, well, he wrote out a very, very long detailed proofs about each of these laws that would take too much time to explain right now. But for the first law, he essentially used 2 equations for force. The first one is from Newton's second law that says a force vector is equal to the mass of an object times its acceleration vector. And the other is the law of gravitation, which says the force vector equals the negative gravitational constant times the mass of the sun times the mass of the planet over the cube of the magnitude of the position vector times the position vector. By setting these equal to each other, Kepler was able to solve for the acceleration vector. His answer told him that the acceleration vector of a planet is parallel to its position vector, and parallel vectors have a cross product equal to 0. So then, he did a lot more fun math with this information, and first showed that a planet moves on an orbit that is in a plane, so it does not move in 3 dimensions. Then he did some more cool math to show that the shape of this orbit is in fact an ellipse. Wow, says Siebel, that was a little confusing, but very cool. You're right, it sounds like, Kepler really knows his stuff. I feel better now. All this talking about fun math made the trip go very quickly because before they knew it, they landed on planet Potato. They found the planet Potato's leader and delivered a document to her with the important message about the universe. It said, "Good news, we have met with the Earthlings and they agreed to let us help them abolish climate change on Earth." Zeeble and Horace are very happy about their successful mission. The end.